Alright, it looks like the microphone is on. We can get into our final video for amplifiers and their kind of simplified circuit. So depending on the input or output criteria that you may have for an amplifier, you may have to look for different or certain impedance profiles. And these impedance profiles really kind of link into that input or output resistance. I know in the last few videos we've kind of been bouncing around between the term is it resistance or impedance, but now we're strictly going to refer to it as impedance. So what we're going to do is consider the impedance profile right here for a voltage amplifier, and we're really going to look at the input impedance and the output impedance. Now we're going to consider this left side of the amplifier, both in the voltage sense, and then we do that pseudo source transform for the current to have a current model of it. Now, if we look at the voltage model here, we know that the input voltage, Vin, to the amplifier, that's going to be equal to this voltage divider between the source voltage right here, the source resistance or impedance, and then the input impedance, Ri, right here. Now, if the input impedance is much, much higher than the source impedance, we can make the approximation that the input voltage is approximately equal to the source voltage, and we would say that we have a high impedance amplifier. If we look at the current modeling of the input here, and we do that pseudo source transform, we know that the input current, In, is going to be that current divider now between the source current impedance and then that combination of the source impedance and the input impedance. Now, if the input impedance is much, much less than the source impedance, so the opposite as what we had here, we can say that the input current is approximately equal to the source current. And that's going to be equal to the source voltage divided by the source impedance. Now, in this case, we have a low impedance network or a low impedance amplifier. So that's how we handle the input impedance. Now for the output impedance, we're just looking at that right-hand side of the amplifier circuit above. And if the output impedance is much, much greater than the load impedance, we know that Vout, or this output voltage right here, is going to be approximately equal to 0, or it's going to tend towards 0. And we can see that in the math here, because if the output impedance blows up, this whole term tends to 0. Now, if the output impedance is much, much less than the load impedance, the output voltage is approximately equal to that open circuit voltage gain multiplied by the input voltage. So we have our cases for high and low impedance for the output. And all this is fine to understand, but if we don't look at an actual circuit, it might not be so useful. Now, what we're going to do is consider the output of an amplifier, and we're just looking at the right-hand side of our voltage amplifier. So we're going to say we have 3 switches here, S1, S2, and S3. 3 output impedances here, Z1, Z2, Z3. We have an output impedance, in this case it's just a resistor. So what we can say is that the output voltage is equal to the open circuit voltage gain times the input voltage, right here as the dependent voltage. And then if we want to look at the output voltage, we have a voltage divider where we're just going to simplify all of our Z1 through Z3, and then we have our output impedance right here. So this is the equation that we have for our output voltage. Now let's say each one of these impedance blocks, Z1, Z2, or Z3, is something like a speaker. And if we disconnect one speaker, we want the other 2 speakers not to be impacted too much. So if S1, or that switch, opens, so that Z1 is now disconnected, our output voltage changes a little bit. Now, inside this voltage divider, we simply have Z2 in parallel with Z3 in this whole term. And this term is not equal to what we had above. So the output voltage is going to be different. And what this tells us is that we have a variable load impedance depending on which combination of these switches are closed or open. So if Z1, 2, or 3 are speakers, or even lights for that case, we know that if the voltage is changing, the current is also going to be changing depending on what switches are open or closed. And that's not really the best thing, especially if we're looking for something like homogeneity in noise output from the whole system or light output from something like the LEDs. So to avoid this, let's say that the output impedance, RO, is going to be much, much greater than Z1, 2, and 3. So what that really tells us is we can make an approximation. Now, if RO is very, very high, that output voltage can be pretty low, and that's might not be optimal. But in the case that it is okay, you don't have that much change depending on the combination of S1, S2, or S3 being open or closed. You still have some, but it's going to be less noticeable and you won't blow up your system. Now, in the previous example, we looked at a high impedance output and it was preferred for the application as long as that voltage for the output doesn't go too low. Now, this isn't always the case, but from the last video, we looked at 4 different kind of amplifiers. So we had our voltage amplifier, our current amplifier, our transconductance amplifier, and our transresistance amplifier. So we have a pretty good sense on how we can use an amplifier in certain applications, but there's really one bread and butter amplifier that we're going to look at, and perhaps it's the most important amplifier for this course, and that's going to be the differential amplifier. So it is quite different from the amplifiers we've looked at above because there's 2 inputs. So in the picture here, where we have this block that represents a differential amplifier, we have an input A and an input B, and we would tie voltages or signals to A and B. So we'd have VI1 and a VI2. Now we have an output voltage, and that output voltage is going to be equal to now something called the differential gain given by A subscript D, and that's multiplied by the difference in those input voltages VI1 minus VI2. Oftentimes you may see this expressed as V subscript ID, which represents the differential input voltage. Then we can say that the output voltage is equal to the differential gain times the differential input voltage. Now inside these differential amplifiers, there's also something called the common mode input voltage gain. And we can also define a common mode input voltage, V subscript I Cm, being equal to VI1 plus VI2 divided by 2. And in reality, the output voltage is the sum of the differential gain multiplied by the differential input voltage plus the common mode gain multiplied by the input voltage or the common mode input voltage. And maybe we're getting a little bit ahead of ourselves, but we can define something as the common mode rejection ratio, and that's going to be in the dB scale, and we define that as CMRR. So in the dB scale, that's going to be 20 log base 10, and then we have the absolute value of the differential gain divided by the common mode gain. But that's enough about the common mode for now. We're going to kind of put that to the side and assume that it's very minimal or negligible for the cases that we're going to be looking at, which are pretty much going to focus on the differential gain. Thank you for watching. If you learned anything new or useful, please like, comment, subscribe. Helps the channel, helps the YouTube algorithm.